Hello, welcome to my next lecture in the Angular Momentum Algebra series. This is my third video in the Angular Momentum Algebra series, and in the previous two videos I have discussed about the different commutation relation among different components of angular momentum of an electron, and in later on we switched to the general momentum case, and we derived the following relations, that Jx, Jy equal to IH cross Jz, and similarly others, Jy, Jz equal to IH cross Jx, and Jz, Jx equal to IH cross Jy, and various other relations we obtained in the last two videos that we will discuss in a short while. But before we start, if you have not watched earlier two videos, you can watch them. I have given the link in the description box. So let's start what we have covered so far. So beside these relations, we have also seen that j square we defined as jx square plus jy square jz square, where j is the generalized angular momentum, which could be j is equal to L plus A in vector notation. In the operator form, I put a hat over it, where L is the angular momentum, S is the spin angular momentum, and J is the generalized angular momentum, which could be angular momentum or spin, which could be orbital angular momentum or spin angular momentum, or the combination of both. So j square equal to jx square plus jy square plus jz square, that we defined, and we also saw that the j square actually commute with jz, jx, jy, and all the components of j. That's why we were able to define a common set of eigenstates for j square and jz, and which we defined as j comma m. We designated this eigenstate by two numbers, j comma n, which are known as quantum number. And the action of j square on this state j comma m, we defined as follows, where small j is a quantum number and capital J is the angular momentum. And for Jz, the z component of the generalized angular momentum on this state, that gives us mh cross j comma m. And we also discussed that the allowed values of m, allowed values of small m for a particular value of a small j is minus j2 plus j in the integer steps, in the integral steps. Okay. For example, minus j plus 1, minus j plus 2, and so on and so forth up to plus j. All right, that's what we discussed, where j could be integer as well as non-fractional, non-integer or fractional in nature. So what we are going to learn today, so far we have seen the action of different operators on this particular state. For example, we also saw what is the action of j plus on j comma m, which was h cross under the root j into j plus 1 minus m into m plus 1 j m plus 1. That is, the action of j plus is to raise m by 1. It doesn't alter j, that we discussed. And similarly for j minus, j comma m was h cross under the root j into j plus 1 minus m into m minus 1 j m minus 1. We also saw that what is the action of jx operator, jy operator on this particular state. Now, having understood all these relations, having established all these relations, now it is good time to have a look on actual matrix representation of this operator for a particular value of a small j. Let's say we choose the value for small j is equal to 1, and then try to see how these different matrices which represent these different operators in the case of small j equal to 1, how they look like. So let's have a look on matrix representation of j square operator for small j equal to 1. So the matrix representation of this j square operator for the small j equal to 1 can be written down with the help of the action that we have defined or we have obtained of j square on j comma m. So if the action of j square on j comma m we have just discussed is nothing but h cross square j into j plus 1, small j into j plus 1, j comma m. Now, if I take this particular equation, suppose I operate this equation by j prime m prime from the left, what we get? We get the following result. The following result will be obtained, which is delta jj prime, delta mm prime, where delta is the Kronecker delta. It means if j equal to j prime and m equal to m prime, only then we get a non-zero value. Otherwise, we will get a zero value for this particular equation on the right hand side. Now, this particular equation helps us in writing down the matrix for j square for a fixed value of a small j. So, let's say we have taken the small value of small j is equal to 1, because this equation itself defines a matrix. If we vary this index for all allowed values of m for a particular value of j, it will create a matrix. We will see how. So, first of all, we will have a look what are the allowed values of m. What are the allowed values of small m? Values of small m for j equal to 1. So, I have just discussed that the allowed values are from minus j to plus j, that is from minus 1 to plus 1 in the integral step, that is minus 1, 0 and plus 1. These are the three allowed values, and we also discussed in the last video that for a particular value of small j, there will be 2j plus 1 allowed values of small m. Now, it means what are the possible states? The possible states are for j equal to 1 and m equal to minus 1, 0 plus 1. The possible states are 1, 1, when j is 1, m is 1, when j is 1, m is 0, when j is 1, m is minus 1. These are the possible states. So, let's write down the matrix representation of j square with all this information having in our mind with the help of this particular equation. So, let's do that. This is the matrix representation of j square. So, we have the states 1, 1, 1, 0 and 1, minus 1. These are the cats. Corresponding bras would be 1, 1, 1, 0, 1, minus 1. And if we want to write down this first element of this matrix, so this will be a 3 cross 3 matrix, because there are 3 values for j equal to 1. So, this is 3 cross 3, 3 corresponding to the cats and 3 corresponding to the bras, 3 corresponding to the columns and 3 corresponding to the rows. So, the first element 1, 1 in the left and 1, 1 in the right. So, when j square operator we get a small j equal to 1. So, we get 2h cross here and delta 1, 1, delta 1, 1, which is 1. Otherwise, for the off diagonal elements from this equation itself, it is evident that off diagonal elements will be 0, because this Kronecker delta will make the element 0. Because suppose for this case we want to check out 1, 0 in the left and 1, 1 in the right. So, 1, 1 in the right will give us delta 1, 1 here, delta 0, 1 here. So, delta 0, 1 will be 0. So, similarly for all the off diagonal terms will be 0. While for the diagonal cases, there will be non-zero case, because both the side will have the same thing 1, 0, 1, 0, 1, 0 on the left, 1, 0 on the right. So, we will get delta 1, 1, delta 0, 0. And the value for j is 1 for all these elements. So, small j equal to 1. So, elements would be again 2h cross square. Here also it will be 2h cross square. Because again j is 1 to 2h cross square, and then for this particular case delta 1, 1, delta minus 1, minus 1. So, that is 1. So, this is the matrix of j square, which can be written as 2h cross square taken out 1, 0, 0, 0, 1, 0, 0, 0, 1. So, this is a diagonal matrix 2h cross square times identity of 3 cross 3. So, this is how the matrix of j square look like for a small j equal to 1. Similarly, if j is not 1, something else like half or something, we can follow the same procedure and write down the same matrix representation of j. Depending upon how many values of m are allowed, that will decide the dimensionality of this matrices. Now, let's have a look at the matrix of jz. Similarly, if we write down the similar kind of equation in case of jz, this is a small j prime, m prime, jz cat j comma m, that will be equal to mh cross delta jj prime delta m prime. It means it is again clear from this equation that the matrix for jz for j equal to 1 or for any value of j for that matter is going to be again diagonal matrix, because off diagonal terms with the help of these deltas will be 0. So let's see those state. So since j equal to 1 is the same, so allowed values of m are same, plus 1, 0 and minus 1, and the states are same, 1 1, 1 comma 0, 1 comma minus 1, and similarly corresponding bras would be 1 1, 1 0, 1 minus 1. So this element 1 1 1 in the left, 1 1 1 in the right, so this will give me delta 1 1, delta 1 1, and since m is equal to 1 here in the right hand side, so this will give me h cross. All the off diagonal terms would be 0. Okay, now what will be this element? 1 comma 0 in the left, 1 comma 0 in the right. So j is small 1, so delta 1 1, delta 0 0, that will be 1, but m is 0 now in the right hand side, so this will be 0. Similarly for this term, if we look out, 1 minus 1 in the left, 1 minus 1 in the right, so delta 1 1, delta minus 1 minus 1, which will be unity, and m in the right is minus 1, so minus h cross. So this will be the matrix, which can be written as h cross outside 1 0 0 0 0 0 0 0 minus 1. This is the matrix representation of jz for j equal to small j equal to 1. Now let's have a look on the other operators, how they look, how their matrix representation look like jx, jy, j plus and j minus. Okay, so if we write down the similar equation for j plus operator, j prime m prime j plus acting on j comma m will give me h cross under the root j into j plus 1 minus m into m plus 1 delta j prime delta m plus 1 m prime. Why? Because the action of j plus on this state we have just discussed, the action of j plus on j comma m will give us h cross under the root j into j plus 1 minus m into m plus 1 j m plus 1. So in the right hand side we will get this kind of a state. In the left hand side there is j prime m prime. If we operate this equation from left, j prime by the bra j prime m prime, so we see that we get delta jj prime delta m prime m plus 1. So this is the equation with the help of which we will actually write down the matrix representation of j plus. This is also clear from this particular equation that there will be non-zeroed off diagonal elements also, because of this mismatch of m prime and m plus 1. Suppose m is 1 in the left, m is 1 in the right, so one will be 2, other will be 1, so that will be 0. But if m is for example 0 in the right and 1 in the left, so this will become 1 1, so this will be unity. So there we have to be careful in the matrix of j plus. So let's write down the matrix of j plus. States are same for j equal to 1 1 1 1 0 and 1 minus 1. Similarly 1 1 1 0 and 1 minus 1. So let's have a look on the matrix element. So for the first case, for the first element, this will be 0 because I've just discussed the diagonal terms will be 0 this time, because in the diagonal terms both m and m prime would be same, but the action of j plus will be such that it will be raise m by 1 in the right. So you are going to get all the diagonal terms to be 0, and in the off diagonal term this will be non-zero, because when j plus act on this, it will raise m by 1 and there is 1 in the left, m equal to 1. So you will get the value h cross, j is small 1, small j is 1, so 1 into 2 is 2 minus m is 0 in the right, m is 0 in the right, so this will give me 0, and delta 1 1 because j and j prime both are 1, and delta m is right hand side is 0 and left hand side m prime is 1, so this is unity. So for this case, if we check out, so m is minus 1, j plus acts on it, it will raise m by 1, it will make it 1 comma 0 kind of a state, and when we see the 1 comma 0 kind of a state with this will again give me 0, because delta, we will get delta 1 comma 0 here. I repeat again, for m minus 1 in the right, so m minus 1 in the right, this will become delta 0, m prime 1 in the left will become 0 1. which will be 0. Similarly, if we check out for this, the j plus acting on this will give 1 comma 2 kind of a state, which will give 0 with this. And however, with this it will give a non-zero value, because when j plus act on this, it will raise m by 1, that is, it will give a state of 1 comma 0 kind of, which is in the left hand side. So we'll get a non-zero value, and the value will be h cross under the root small j is 1, 2 minus m. M in the right is minus 1. So when I put minus 1 here, so this will give me again 0. In this case, again, if I see that 1 comma minus 1 in the left, 1 comma 1 in the right, j plus acting on this will raise m by 1. That will give a kind of a state 1 comma 2, which will give 0 with this. Similarly, in this particular case, m with j plus act on this, it will raise m by 1. So it's going to give 1 comma 1 kind of a state. With this, it will give me a 0, which is equal to, can be written as h cross root 2 or root 2 h cross 0 1 0 0 0 1 0 0 0. Now let's write down the matrix representation of j minus for j small j equal to 1 case in the similar fashion the way we have written down the matrix representation for other operators. Now for this particular case, in case of j minus, when we write down the same equation, so this gives me this value here. This is m minus 1, mind you. Earlier it was m plus 1 in case of j plus, and delta jj prime, delta m minus 1 m prime. Earlier it was delta m plus 1 m prime. States are same, so I have written down here. And let's see this. What is the first element? Before we do that, we realize by having a look on this particular equation that again I'm going to get all the diagonal elements to be 0, because for diagonal elements both m and prime would be same, while this particular delta, canonical delta, assures us that for same m and m prime this is going to be 0, because delta m minus 1 is sitting there. If I take m and m prime both to be 1, for example, so this will be delta 0, delta 0 and 1, which will be 0. So ultimately all the diagonal elements will be 0, but of diagonal elements we are expected to get value. Let's check out. For this particular element, 1 comma 1 in the left, 1 comma 0 in the right, so this will become delta minus 1, because this will lower down, j minus will lower down m by minus 1, and this is m equal to plus 1 sitting in the left, so this will be 0. While for this particular case, again, if you see, j minus will lower down by minus 1, which is not allowed, so this will give 0, because minus 1 is the lowest value. How about this? This is 1 comma 0 in the left and 1 comma 1 in the right. So in the right there is m equal to 1, and j minus acts on this, and it gives a state of the kind 1 comma 0. So 1 comma 0 in the left, so it is expected to give non-zero value, and the value will be h cross under the root small j equal to 1. So this will be 2 minus m in the right is 1. So if I put m equal to 1 here, so this second term under the root will give me 0, and delta 1 1, and delta m is 1 here, so delta 0 comma m is 0 in the left, delta 0 0, which is 1. So this is that. Now for this particular case, again we'll get a 0 value because j minus will lower down the value of m by 1, and we will get a state of 1 comma minus 2 type, which is not allowed for j is equal to 1, so this is 0. For this particular case, 1 comma minus 1, we will see that j minus acting on this will give me 1 comma 0 kind of a state, which is 1 minus 1, and the cat will be something of 1 comma 0 type. So this is going to be give me 0 from this particular equation. Okay, and for this state 1 comma 0 in the right and 1 comma minus 1 in the left, j minus 1 act on this will reduce down the m by 1, and we get a state of 1 comma minus 1 type. So we are going to get non-zero value, and the value is h cross under the root 2 minus, now m is 0, so this 0 will make it 0, so this is it. So what we get is the matrix representation of j minus as under root 2 h cross 0 0 0 1 0 0 0 1 0. That is the matrix representation of j minus for special case small j equal to 1. So after having a look on the matrix representation for j plus j minus, j square and jz, now let's look at the matrix representation of jx and jy operator. So jx operator, we know that from the previous two videos that we had discussed in these two videos, that a j plus is defined as jx plus iota jy, and j minus is defined as jx minus iota jy. So from these two equations, jx is actually half of j plus j minus, and jy is 1 over 2 iota j plus minus j minus. So we'll use these two particular equations to find out the matrix representation of jx and jy respectively. So for jx, we'll write down, if we write down the similar kind of equation, the j prime m prime bra and the in the right hand side the cat j comma m, what we get is the following: half of j prime m prime j plus j minus j comma m. So when j plus act on this, we'll get a value, and other state, and j minus act on this, we get a value of this state. Let me write down the result straightforward, which is easy to understand now because we have extensively discussed the action of j plus and j minus on j comma m state. Delta j prime delta m prime m plus 1 plus h cross by 2 under the root j plus 1 minus m minus 1 delta j prime delta m minus 1 m prime. Okay, so that's what we get. When for the matrix representation of jx, we have to write down this equation, and now we can write down the matrix representation jx as, because the states are same, the allowed values of m are again 1, 0 and minus 1. One comma 1, 1 comma 0, 1 comma minus. So for the first element, if we look at, so in the right hand side again we get 1 comma 1, and the left side 1 comma 1, which both these will make it 0 because of the same logic that we have been discussing in case of j plus and j minus. So you are expected to get all the diagonal elements to be 0. For off diagonal elements, however, if you see the 1 comma 0 in the right, 1 comma 1 in the left, so when j plus act on this, so this will give me 1 comma 1 kind of a state, we are going to get non-zero value, but when j minus act on this, we are going to get 0 value, because we will get a state 1 comma minus 1 kind of, which will give 0 with this. So for this particular element, this will contribute as in the non-zero value of this element, while this will be 0. From this portion, we will get the value h cross by 2, and j is 1, so under root 2. And from here m is 0, so I will get 0 value here, and delta jj prime delta 1 1, and delta m prime is 1 and m is 0, so it's again 1, so this will be 1. However, for this particular case, if we look at, so if when j plus act on this, it will raise the m by 1, so which will give 0 value with this. The first term will give me 0 value. However, from the second term we'll look at our j minus act on this, again it will give me 0. For this particular element, j plus acting on this will give me some 1 comma 2 kind of state, which is not allowed because the allowed values are 1 comma 1, 0 and minus 1, so this will be 0 from the first term. In the second term, however, when j minus act on this, it will give 1 comma 0 kind of a state, which is presented in the left, so this is expected to give a non-zero value, and the value will be h cross by 2 under the root 1 into 1 plus 1, that is 2, minus, now m equal to 1 in the right, so when I put m equal to 1 in the right, it will be 0, and delta 1 1, because j are 1 in both the cases, and delta m minus 1, which is delta 0, and m prime is already 0, so if we check out this for this element here, so when j plus act on this, it will raise m by 1, so it will give a kind of a state 1 comma 0, which is present in the left, so it is expected to give non-zero value. However, in case of j minus acting on this will reduce down the value of m by 1, which is not allowed because the allowed values are 1 0 minus 1, so the second term gives me 0, the first term will give a non-zero value, and the value will be h cross by 2 under the root 2 minus 0, because if I put m equal to minus 1 here, so this m plus 1 will make it 0. Okay, similarly, if we look for this element here, 1 comma 1 right, when j plus act on this, it will give you 0, and j minus act on this, it will give you a state of 1 comma 0 kind of state, which will give 0 with this. Similarly, if j plus act on this, So this will give me 0 with this. When j minus act on this, it will expect it to give a non-zero value, and the value will be h cross by 2 under root 2, and m is 0 here. So this will make it 0, and that's it. So this is the matrix representation of j plus for small j equal to 1, which can be written as h cross by root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. So that's what we get for jx. Similarly, we can do the same exercise for jy, and let's see what we get. Matrix presentation of jy, we will write down the same equation. Jy is sitting here, so this jy is j plus minus j minus upon 2 iota, which I have written down here. And now we can further write down what's this value. This will give value as 1 over 2 iota, and j plus acting on this will give me h cross under the root j into j plus 1 minus m into m plus 1 delta jj prime and delta m prime m plus 1. Similarly, when j minus act on this will give me 1 minus 1 or 2 or iota is from this, and h cross under the root j into j plus 1 minus m into m minus 1 delta jj prime delta m prime m minus 1. This is m prime m minus 1. So let me write down clearly. This is delta m prime m minus 1. Okay, so what we get is, for jy matrix, we get 1 1 1 0 1 minus 1 1 1 1 0 1 minus 1. This is m prime m minus 1. So let me write down this thing into delta m prime m minus 1. Okay, so let's see. So again, the diagonal terms would be 0, because for diagonal terms both are same, jj prime and mm prime are same. So these two canonical deltas are m prime m plus 1 and m prime minus 1. So the diagonal terms would be 0. Off diagonal terms we will see. So 1 comma 1 in the left, 1 comma 0 in the right. When j plus act on this, it will raise the m by 1 and we'll get a non-zero value. We'll get a non-zero value from the first term, while from the second term, when j minus act on this, we'll get a minus 1 comma minus 1 kind of a state, which will give 0 with this. So from the first term in this equation, we get a non-zero value, and the value is h cross upon 2 iota under the root 2 minus m is 0, so it will make it 0. Okay, in this case, when j plus act on this, it will give me 1 comma 0, which will give 0 with this. When j minus act on this, will give 0. So this is 0. For j plus act, when j plus act on this, so this will give me 0. The first term will give me 0. When j minus act on this, it will give me 1 comma 0 kind of a state, which is present in the left. So I will get a non-zero value, and the non-zero value from the second term would be minus h cross upon 2 iota under the root 2, because j is 1, 1 into 1 plus 1, minus m is 1 in the right. So when I put m equal to 1, so this second term under the root will be 0. So this is it. Now for this particular element, when j plus act on this, it will give me 1 comma 0, which is present in the left. So I will have a non-zero value. When j minus act on this, that will give me 0. The second term will give me 0. J plus acting on this will give me non-zero value, which is the first term, and the non-zero value is h cross upon 2 iota under root 1 into 1 plus 1, that is 2, and j is equal to m is equal to minus 1 here, so this will be 0. Similarly, for this particular term, this particular element, 1 comma minus 1 in the left, 1 comma 1 in the right. When j plus act on this, this will give me 0. When j minus act on this, this will give me 1 comma 0 kind of a state, which is gives 0 with this. Similarly, when j plus act on this, it give me 1 comma 1 kind of state, which will give 0 with this because of this canonical delta. And when j minus act on this, this will give me 1 comma minus 1 kind of state, which will give me non-zero value because of this canonical delta, and the value will be minus h cross upon 2 iota under the root 2, and m is, we get the matrix representation for small j equal to 1 case as follows, as this: 0 1 0 minus 1 0 plus 1 0 minus 1 0, which can be further written as h cross by 2 0 1 over iota inside, which is minus iota 0 this can be written as iota square, 1 over iota will make it iota, 0, again 1 over iota will make it minus iota, and 0, and again this can be written as iota square divided by iota, which is iota, and this is 0. If we wish, we can write down this matrix as this also. After having looked on the representation, matrix representation of these various operators, j plus, j minus, jx, jy, jz, j squared, now it is good time to see that how this states j comma m for particular values of j and look like in their matrix representation, or how they what are these states basically on which we will act these operators, which are nothing but the matrices of 3 cross 3 order. So this, according to the Dirac notation, the states of quantum states are represented generally by the column vectors. So we would like to see how these column vectors, these column matrices look like in the case of, for example, if we take the eigenstate of Jz, which is nothing but j comma m that we have been taking so far. This is the common eigenstate of j square and j comma m. So let's have a look on that, how this j comma m state look like. So for small j equal to 1 and m equal to -1 0 plus 1 or +1 0 -1, 3 possible states. The states possible are one, we have been discussing it, 1 1 and 1 0 and 1 minus 1. So how they look like in their matrix representation. So let's try to look on that. So suppose the state, the eigen value of jz which we have been taken is, we have been taking so far, j comma m, and the values are m h cross j comma m. Suppose this is completely unknown to us, and let's suppose that this is nothing but some kind of a column vector a, b, c, because we have seen jz is a 3 cross 3 kind of a matrix, and this has to be a column vector, and 3 cross 3 has to act on 3 rows, and the column vector means it has one column only, so it has to be of 3 cross 1 type. So we have taken to be, let's say, a, b, c. So the action of jz now on this a, b, c will be m h cross a, b, c back. This is the eigenvalue equation for jz. Okay, so now m has 3 allowed values, +1 0 and -1. So basically this particular equation is a set of 3 equations which will give us different values of a, b, c, which will help us to find out the values of a, b, c. Let's find out them. So for m equal to +1 case, this equation gives us jz acting on a, b, c will give me +1 h cross a, b, c back, because this is eigenvalue equation, and jz, the matrix representation for jz in case of j1 jz, we have just written that it was h cross 1 0 0 0 0 0 0 0 -1. We had just found out that, and this is a, b, c and h cross a, b, c. So h cross cancels h cross, and what we get as a 0 minus c is equal to a, b, c. So from this we conclude that a equal to a, b equal to 0 and c equal to minus c, which implies c is equal to 0. So from this values, what we see that a is arbitrary. A is arbitrary. A can have any value, because for any value of a, this condition will be satisfied, a equal to a. While b and c have been fixed by this particular equation, that is both are 0 0. So for this case, m equal to 1, j equal to 1, for the eigenvalues m equal to +1 case, so what are the possible eigenstates for jz? The possible eigenstates of jz are a 0 0, where a could be anything. It could be like 1 +1 -1 or any other value. Alright, so for, let's say we choose one particular value, and let's say this is 1. So this state would be 1 0 0 kind of column vector for small j equal to 1. Okay, so similarly we'll see for another value, and let's see that what we get at j comma m as column vector in the case of m equal to 0, for eigenvalue m equal to 0 case. So for m equal to 0 case, the eigenvalue equation of jz will read as 0 a, b, C. And Jz matrix representation for small j equal to 1 case that we have been discussing, Jz we have just discussed was h cross 1 0 0 0 0 0 0 0 minus 1 a b c 0 a b c. So this equations gives me a 0 minus c is equal to 0 into a b c, which is equal to a equal to 0 into a, 0 equal to 0 into b, and minus c equal to 0 into c. This equation gives me this. So from this it is clear, so that a equal to 0 into a. So whatever we choose the value of a, so this a will make it 0. So this a is 0 from here. And for this case, minus c equal to 0 into c. Whatever the value of c you choose, again this will make value of c 0. But for this particular equation, so 0 equal to 0 into b, whatever the value of b we choose here, it will give us left hand side is 0, right hand side will also be 0, but b becomes arbitrary because we could have any value there. However, if we choose any value of a, this will imply that a is nothing but 0. If you choose any value of c, this equation will imply nothing but c is 0. But this equation tells us b is arbitrary. And b is arbitrary, it means we can have any value, and the value, let's we take is for the simplicity, let's say b equal to 1, let b equal to 1. So for the case m equal to 0 eigenvalue, cat j comma m, which is equal to cat 1 comma 0, looks like 0 1 0, or in general 0 b comma 0, but for particular value of b equal to 1, it will be like 0 1 0 1 0. Similarly, we can find out the column vector for m equal to minus 1 case. For m equal to minus 1 case, we will get the eigenvalue equation as a b c minus 1 into h cross a b c. Jz is h cross 1 0 0 0 0 0 0 0 minus 1 a b c minus h cross a b c, which will give me a 0 minus c is equal to minus a b c, which means a is equal to minus a, b equal to 0, and minus c equal to minus c. So from this we see that a is 0, from this we see that b is 0, and from this c is arbitrary because this is true for any value of c, that minus c is equal to minus. So we choose again for simplicity or c equal to plus 1. So for m equal to minus 1 eigenstate, j comma m is equal to j is 1, m is minus 1, that is equal to 0 0 minus 0 0 c, and in general, and for particular value of c equal to 1 0 0 1. So that's what we get. So we get all these three states. So let me write down what we have got so far. Representation for this cat j comma m for different eigenvalues. For m equal to 1 case, m equal to plus 1 case, we get 1 comma 1. If you remember, we get 1 0 0. That's what we got. M equal to 0 case, this become 1 comma 0, and this what we get 0 1 0. And for m equal to minus 1 case, this 1 comma minus 1, which is equal to 0 0 1. So that's what we get as three states. Remember, these are the eigenstates of operator Jz, and these were nothing but the common eigenstates of j square and so on. So these are the eigenstates of j square also, because the j square and jz both have common eigenstates that we have been taking since last video, that they have been common eigenstates of as j comma m. So these are the eigenstates of j square also. So in this video we have learned that how to write down the matrix representation of different operators, j square, jz, j plus, j minus, jx, jy, jz, and how to find out their corresponding eigenstates. In the next video, we'll discuss more about the angular momentum. Thank you so much.